We'll start in a minute. Today we'll cover the last two sections, 10.6 on parametric equations and 10.8 on vectors. Okay, on parametric equations, we read here the position and direction of an object in space, 3 dimensions, or in a plane, which is 2 dimensions, at time t can sometimes be modeled by parametric equations, which are functions of the parameter t, or t often represents time. So we let f and g be functions of t over an interval I. Then the set of points, xy coordinates, where the x coordinate is f of t and the y coordinate is g of t, that set of points is called a plane curve. The equations x equals f of t and y equals g of t are called parametric equations of the curve, and the variable t is called the parameter. So here's our first example. Write parametric equations for the curve defined by y equals x plus 2 with the given definition of x. Then sketch the curve and indicate by arrows the direction, also called the orientation of the curve. First note, we recognize y equals x plus 2 as a linear function of y. The graph of y equals x plus 2 is a straight line with slope positive 1 and a y-intercept of 0, 2. Okay, but we're going to write parametric equations. First, if x equals 3t, then we replace x in this equation with 3t. So y is equal to 3t plus 2. Okay, then we're going to sketch the curve based upon these parametric equations. And as you'll see, there will be an orientation or a direction. So I'll create a table. I'll have t values in the left column, x values or x coordinates in the middle column, and then y coordinates on the right. So if we start with t equals -1, then the x coordinate is 3 times -1 or -3. And the y coordinate, 3 times -1 plus 2 is -1. Then when t is 0, x is 3 times 0 or 0. And the y coordinate, 3 times 0 plus 2 is 2. And then let's pick t to be 1. The x coordinate is 3 times 1 or 3. And the y coordinate, 3 times 1 plus 2 is 5. Okay, so we'll plot those points in the xy plane. We're going to plot the x and y coordinates. So when x is -3, the y coordinate is -1. So that's the ordered pair -3, -1. The next ordered pair is 0, 2. So 0, 2. And then the third ordered pair is 3, 5. So here is the ordered pair 3, 5. Okay, well, the values of t determine the direction. So our smallest value of t starts out at the point -3, 1. And then as t increases, the direction of the curve is like this. So I indicate using arrows the orientation or the direction of this straight line. Well, being able to parameterize a curve like this is useful in such subjects as physics. If you're tracking a particle that's moving along a straight line, then you can indicate by a parameterization what the direction of that particle is along the line. You can also, by the way that you parameterize it, you can also indicate what the speed of the particle is. Okay, our second example, still using y equals x plus 2. This time we assign x to be -t. And so if x is -t, y is equal to -t plus 2, because we replace x with -t. So we'll do the same sort of thing that we did a few minutes ago. We'll pick some t values. We'll determine what the corresponding x and y values are based upon the parameterization. So let's just use the same t values, -1, 0, and 1. When when t is -1, x is the negative of -1, which is 1. And y is the negative of -1 plus 2, which is 3. When t is 0, x is 0. And y is positive 2. And then when t is 1, the x coordinate is -1. And the y coordinate, -1 plus 2, is positive 1. Okay, so we'll plot the x and y coordinates that we found. We have the ordered pair 1, 3 that corresponds to t equals -1. Then we have the ordered pair 0, 2. And then thirdly, we have -1, positive 1. -1 for x, positive 1 for y. But this time, even though the line is the same line, the orientation is reversed. And we could also say that if this represents a particle, it's moving slower than it did for the curve on the left, or for the straight line on the left. Okay, next example. Let's parameterize the curve given by y equals x squared minus 4x plus 3. so that t equals 0 corresponds to x equals -1. Well, there's more than one way to do it. As you saw in the previous examples, we just considered two different parameterizations of the same line. They each had different directions and different speeds. So this curve we recognize as a parabola, y equals x squared minus 4x plus 3. But we just want a parameterization so that when t is equal to 0, we get an x coordinate equal to -1. So one way to do it, I'll just pick the simplest one of all. We'll pick x to be t minus 1. And then you can verify that when t equals 0, x is -1. That's what we want. Okay, but we want y to be defined in terms of t also. But since x is equal to t minus 1, in this equation, y equals x squared minus 4x plus 3, we just replace x with t minus 1. So y equals t minus 1 squared minus 4 times t minus 1 plus 3. And we'll do the arithmetic, I should say algebra and arithmetic, to simplify y as much as we can. So we get, when we square t minus 1, we get t squared minus 2t plus 1. And then minus 4 times the quantity t minus 1 is minus 4t plus 4 plus 3. And so we get y equals t squared minus 6t plus 8. Okay, so we'll create a table of t, x, and y values. This time we'll start with t equals 0. When t is 0, x is -1, and y is +8. And then we'll pick a few more t values. Whoops, I want to go from 0 to +1, and then we'll go 2, 3, 4. We'll see what we have after t equals 4. When t is 1, x is 0, and y is 1 minus 6 is -5. -5 plus 8 is 3. When t is 2, the x coordinate 2 minus 1 is 1, and the y coordinate 2 to the second is 4 minus 12 is -8. -8 plus 8 is 0. When t is 3, the x coordinate is 3 minus 1 or 2. The y coordinate 3 squared is 9. Minus 18 is -9. -9 plus 8 is -1. When t is 4, x is 4 minus 1 or 3. The y coordinate 4 squared 16 minus 24 is -10. -10 plus 8 is -2. So let's pick x or t to be 5. When t is 5, x is 5 minus 1 or 4. And then 5 squared is 25. Minus 30 is -5. And -5 plus 8 is 3. So I'm thinking I made a mistake somewhere. Let's see. When t is 3, 9 minus 18, -9 plus 8. So that one's right. When t is 4, 16 minus 24 is negative 10. Negative 10 plus 8 is negative 2. So something doesn't look right. But let's try plotting these points, just the x and y coordinates. So the x values are ranging from negative 1 up to 4. So negative 1, 8, 0, 3, 1, 0, 2, negative 1. Yeah, there's something wrong with this one. What am I doing wrong? 3 squared is 9. Minus 18 is negative 9. Negative 9. Yeah, so oh, sorry. When t is 4, 4 squared is 16. Huh. This worked when I did it when I was practicing. So anyway, I'll send you later a corrected one, but it's the direction of the curve is like this. So let's move on for now. Okay, this one, find two different sets of parametric equations to model x squared plus y squared equals 9. You'll recognize this as the standard equation of a circle centered at 0, 0 with a radius of 3. So if you graph the circle, looks something like this. So we can find any number of sets of parametric equations for x squared plus y squared equals 9. We just want to find two. So if I pick x to be 3 times cosine of t, and if y is sine, y is 3 times sine of t, and if I pick my t values between 0 and 2 pi, this will parameterize this circle. So let's just pick a few points. We're going to start with t equals 0. Cosine of 0 is 1. 3 times 1 is 3. And then for the y coordinate, 3 times sine of 0 is 0. Okay, so our first point is the ordered pair 3, 0. Well, let's just pick t to be pi over 2. We could pick intermediate values like pi over 6 and pi over 3. But let's just jump to t equals pi over 2. Cosine of pi over 2 is 0, so 3 times 0 is 0. For sine, sine of pi over 2 is 1. 3 times 1 is 3. So we get the ordered pair 0, 3. So the direction of the curve is counterclockwise. And then let's pick t to be pi. Cosine of pi is negative 1. 3 times negative 1 is negative 3 for the x-coordinate. Sine of pi is 0, so 3 times 0 is 0. So let's see, this one is 0, 3. Now we're at this point, which is negative 3, 0. So the orientation continues counterclockwise. So a couple more points for t. T is 3 pi over 2, and then we'll end at 2 pi. 3 pi over 2, cosine of 3 pi over 2 is 0. So the x-coordinate is 0. Sine of 3 pi over 2 is negative 1. 3 times negative 1 is negative 3. And then 2 pi, cosine of 2 pi is 1. 3 times 1 is 3. And sine of 2 pi is 0, so we get 0. So corresponding to t equals 3 pi over 2, we have this point, 0, negative 3. And then at 2 pi, we complete one revolution. Okay, a second set. Well, we could just pick x to be 3 times sine of t, and y we could pick to be 3 times cosine of t. So if we do this one, when t is 0, the x-coordinate is 0. So on this one, the starting point is at 0, 3. And then let's just figure out what the orientation is. We won't graph the whole thing, but so we pick t to be 0. T is 0, the x-coordinate is 0. The y-coordinate is 3. So if we pick t to be pi over 2, well, sine of pi over 2 is 1. 3 times 1 is 3. And cosine of pi over 2 is 0, so 3 times 0 is 0. So when we go from t equals 0 to pi over 2, the curve on the circle goes from 0, 3 to 3, 0. So for this parameterization, we have a clockwise direction or orientation. Okay, let's look at the next example. The first part of this next example is similar to what we've been doing, but we're also, in addition to that, we're going to eliminate the parameter and write the parametric equations as a Cartesian equation. This time we're going to limit the t values so that they're between negative 2 and 3. So we'll pick the t values just to be integers. So starting at t equals negative 2, and we'll range up to t equals 3. Okay, so the x-coordinate, when t equals negative 2 squared is positive 4, minus 2 times negative 2, so 4 plus 4 is 8. And the y-coordinate, -2 minus 2, is -4. When t equals -1, -1 squared is 1. 1 minus 2 times -1 is the same as 1 plus 2. So the x-coordinate is 3. And then for the y-coordinate, -1 minus 2 is -3. When t is 0, the x-coordinate is 0, and the y-coordinate is -2. When t is 1, the x-coordinate is 1 minus 2, or -1. And the y-coordinate, 1 minus 2, is -3. When t is 2, x is 2 squared, which is 4, minus 2 times 2, so 4 minus 4 is 0. And the y-coordinate, 2 minus 2, is also 0. And finally, when t is 3, the x-coordinate, 3 squared is 9, minus 2 times 3, 9 minus 6 is 3. And the y-coordinate, 3 minus 2, is 1. Okay, so in the xy plane, we will plot the x and y coordinates. So we're starting over where where x equals 8. So the ordered pair, 8 for x and -4 for y. This is the first point. The next ordered pair, 3, -3. So 3, -3. 0, -2. -1, -3. So did I foul up again? Let's see, when t is 1, no. So the orientation is, just doesn't look right. 0, 0. Let's plot 0, 0. Oh. Yeah, here's my mistake. When t is 1, 1 minus 2 is -1. Okay, that makes me feel better. So -1, -1. 0, 0, and then finally 3, 1. Okay, so this was our first point. So the orientation is moving in this direction. So just put 2 or 3 arrows to indicate the orientation. Okay, then the second part, eliminate the parameter. The parameter is t, and then write the parametric equations, combine it so it's just a single Cartesian equation. So down here, I'll just rewrite the parametric equations. X equals t squared minus 2t, and y equals t minus 2. There are often multiple ways to write a Cartesian equation. But if you can easily solve for t in one of the equations, it looks like if we solve for t in this one, t equals y plus 2, that is pretty obviously easier than solving the other equation for t. So from this equation we solve for t, we get t equals y plus 2. So in the other equation, we're going to replace t with y plus 2. So x equals the quantity y plus 2 squared minus 2 times y plus 2. Then we do the algebra and arithmetic. So we get x equals, when we square y plus 2, we get y squared plus 4y plus 4, then minus 2y minus 4. And then simplify, we get x equals y squared plus 2y. This is our Cartesian equation. By Cartesian, it is meant that it's expressed in terms of x and y. Okay, well, again, the difference between the Cartesian equation and the parametric equations is the Cartesian equation does not indicate any orientation. So that is one of the great uses of being able to parameterize equations. Okay, let's move on to the next page. Okay, we'll do some exercises where we eliminate the parameter t and write the parametric equations as a Cartesian equation. So if it's not too hard, I'll parameterize, or I'll get rid of the parameter in more than one way. So on this one, if we solve the first equation, x equals 3t minus 1, solve this for t. So if we add 1 to both sides and divide both sides by 3, we get t. And then in the other equation, we'll just replace t with x plus 1 over 3. And this is an okay answer. We know how to expand this, so this is okay. Just leave it in this form. Okay, that's one way to do it. Another way, suppose we want to solve the equation on the right for t. So if we first divide both sides by 2 and then take the square root of it, well, we get positive and negative equals t. And then in the other equation, we write x equals positive and negative 3 times the square root of y over 2 minus 1. So if I had to choose which one of those I would like the best, I think this one would be my choice. Okay, but they're equivalent, so just pick the one you like. All right, the next one. This time we have x equals e to the t and y equals 2 plus 3t. So eliminate the parameter t. Well, one way to do it, solve x equals e to the t for t. So if we take the natural log of x, or the natural log of both sides, the natural log of x equals the natural log of e to the t. But the natural log of e to the t is equal to t times the natural log of e. The natural log of e is 1, so we get t equals the natural log of x. So in the other equation, we just replace t with the natural log of x. So we get y equals 2 plus 3 times the natural log of x. Okay, that's one way to do it, but there's a second way to do it. This time we will solve y equals 2 plus 3t for t. So subtract 2 from both sides and then divide by 3. We get y minus 2 divided by 3 equals t. And then in the other equation is we're starting out with x equals e to the t. We just replace t with y minus 2 over 3. So I really like logarithms, so I might choose this one, even though the other one is just as good, I guess. Okay, let's try another one. So in this one, we have x equals log base 10 of t. Remember, a logarithm, if it doesn't specify the base, it's assumed to be a base 10 logarithm. So if we solve x equals the base 10 logarithm of t for t, well, we just get t equals 10 to the x to the power x. And then we can write y equals the square root of 10 to the x minus 1. Okay, alternative, solve y equals the square root of t minus 1 for t. So square both sides, and then add 1, we get y squared plus 1 equals t. And then in the other equation, we can write x equals the base 10 logarithm of y squared plus 1. So you might remember from college algebra, finding inverses of exponential equations, which involve logarithmic equations, and vice versa. So in all of these examples where I've been finding two ways or writing two different ways to eliminate the parameter, we're just using the process of same kind of process that you would follow if you're trying to find the inverse of a function. Okay, the next one, this is something new for today. This says parameterize the straight line segment from the point whose coordinates are 1, 2 to a second point whose coordinates are 3, 5. And we're going to parameterize the straight line segment so that the t-values are between 0 and 1. So this isn't really that hard to do, but it's a useful thing to remember I guess everything that we cover is useful to remember, but how do we do that? Well, the point that we're starting from is the ordered pair 1, 2. So t equals 0 has to correspond to the ordered pair 1, 2. And then as the values of t increase between 0 and 1, we're going to hit all of the other points that are between the ordered pair 1, 2 and the ordered pair 3, 5 on a straight line segment. Okay, so for each of the points on that straight line segment, each one of those corresponds to an ordered pair xy. So we're starting out, the first point, or the initial point, is the ordered pair 1, 2. Okay, and we're going to multiply the ordered pair by a scalar, something that represents a real number. And we're going to multiply each of the coordinates by the scalar. Okay, so I know that if I multiply each of the two coordinates by 1, then I just get the coordinates. That's what I want to do to start with. And so if I just write 1 minus t, when t is 0, I'm just at the point 1 times the ordered pair 1, 2. But as t increases between 0 and 1, I want to end up at the other point, 3, 5, when t is equal to 1. So in this bracket, I'm going to put t. So let's write the ordered pair. So 1 times 1 minus t for the x-coordinate is 1 minus t. And then I'm adding that to the x-coordinate 3 times t. We'll simplify this in the next step. Then the y-coordinates, I have 2 times the quantity 1 minus t. So I get 2 minus 2t. And then plus 5 times t. So now let's simplify. 1 minus t plus 2t is 1 plus 2t. And the y-coordinate, 2 minus 2t plus 5t is 2 plus 3t. And this is for values of t that are between 0 and 1. So notice that this x-coordinate, 1 plus 2t, is a linear expression because the variable on t is 1. And the expression for the y-coordinate is also linear. So for values of t between 0 and 1, if we plot all of the x and y coordinates, we're just going to get a straight line segment. So let's just check. When t is 0, the x-coordinate is 1, and the y-coordinate is 2. That's what we want. We want to start at the ordered pair 1, 2 when t is 0. And then finally, when t is 1, well, the x-coordinate when t is 1 is 1 plus 2 times 1, or 3. And the y-coordinate is 2 plus 3 times 1, or 5. And sure enough, when t is 1, the endpoint is 3, 5. Okay, if you want to find other points that are on the line segment, just pick values of t that are strictly between 0 and 1. Okay, that's how you parameterize a straight line segment. Well, if you want the interval to be between 0 and 1. Okay, a few more exercises. Let's rewrite the parametric equations by building an XY table. So in other words, well, in addition, we want to find the Cartesian equation for the curve that has these parametric equations. So we'll construct an XY table involving t values, and then we'll see if we can determine what a formula is in terms of x and y. So let's just start with t equals 0. When t is 0, x is -1, and y is +4. When t is 1, the x-coordinate is 2 minus 1 or 1, and the y-coordinate is 5. When t is 2, the x-coordinate is 2 times 2 minus 1 is 3, and the y-coordinate 3 plus 4 is 7. Sorry, I'm adding the wrong numbers. When t is 2, the y-coordinate is 2 plus 4, which is 6. So I didn't foul up the other ones, did I? No. Okay, so we have enough information. We can tell by looking what sort of equation represents the x and y coordinates. Notice that as the x values increase by 2, from -1 to 1, that's an increase of 2, and from 1 to 3, it's an increase of 2. The y coordinates increase by the same amount, 1. So this tells us that the Cartesian equation is a linear equation. So we can pick two of the ordered pairs and find the slope of the line that passes through them. So remember the slope formula. Slope formula, y2 minus y1 divided by x2 minus x1. So I'll pick y2 minus y1 to be 6 minus 5, and x2 minus x1, 3 minus 1. So I get 1 over 2. So the slope of the line is 1/2. And then remember the point slope form. If I know the slope of a line and one ordered pair on the line, then I can write the point slope equation. We have 3 points to choose from. So pick any one of those 3 points. So the point slope form. The point slope form is y minus y1 equals the slope m times x minus x1. So I'll pick this ordered pair 1, 5. So y minus 5 equals 1/2 times x minus 1. So this is a good enough equation if you want to leave it just like that. But you could also solve it for y. So y minus 5 equals 1/2 x minus 1/2. And then if you add 5 to both sides, you get y equals 1/2 x plus 9/2. So there's our Cartesian equation. The next example is similar. I'll leave this other one for you to do. And we know how to parameterize a line segment from a starting point to an ending point. If the first point corresponds to t equals 0 and the second point corresponds to t equals 1. So let's just write down what that is, x, y. Well, let's see, the initial point is 2, 3. That corresponds to 1 minus t. And then the end point, 6, 1. Times t. So the x and y coordinates, 2 times 1 minus t is 2 minus 2t, and then plus 6t. And then the y coordinate, 3 minus 3t plus t. We'll simplify a little bit more. The x coordinate, 2 minus 2t plus 6t, is 2 plus 4t. And the y coordinate, 3 minus 3t plus t, is 3 minus 2t. Yeah, and that works out. You can check when t is 0, the ordered pair is 2, 3. And when t is 1, the ordered pair is 6, 1. Okay, the last one, though, is a little more challenging, but it's not too bad. This time we'll parameterize the line segment from 2, 3 to 6, 1, so that 2, 3 corresponds to t equals 0, and 6, 1 corresponds to t equals 2. Okay, so the t values go from 0 to 2 this time. So what do we do now? Well, it's not too hard, really. So we're going to multiply the initial point, 2, 3, by 1 minus t divided by 2. And then the end point, 6, 1, we're going to multiply that by t divided by 2, which is what we want, because when t is 2, 2 over 2 is 1. So we'll simplify a little bit more. So the x-coordinate, 2 times 1, and then minus 2 times t over 2 is just minus t, plus 6 times t over 2 is plus 3t. Then the y-coordinate, 3 minus 3t over 2, plus 1 times t over 2. And then simplify a little bit more. The x-coordinate, 2 minus t plus 3t, is 2 plus 2t. And 3 minus 3t over 2 plus t over 2 is 3 minus 1t, or just 3 minus t. This is for values of t between 0 and 2. Yeah, so let's just visually check. When t equals 0, the ordered pair is 2, 3. That's what we want to start with. And when t is 2, 2 plus 2 times 2 is 6. And 3 minus 2 is 1. That's our endpoint. So everything checks out on this one. Okay, let's start the section 2.8 or 10.8. So section 10.8 is on vectors. Okay, a vector is a quantity that is described by both magnitude and direction. A vector in a plane is a line segment with an arrow on one end to specify the vector's direction, and the length of the vector is the magnitude. So if we let P and Q be points in a plane with an arrow pointing from point P to point Q, then we can denote this vector by writing PQ with an arrow, a rightward arrow on top. The notation itself indicates that the point P is the initial point and point Q is the terminal point. And then the magnitude of the vector PQ is denoted by the absolute value of the vector PQ, which is the length of the vector. Okay, so if we have a point P and another point Q in the plane, then the initial point of the vector at P and the terminal point at Q, and the arrow indicates the direction, we can denote that vector by using this symbol, PQ with a rightward arrow. So this is the vector PQ. And the length is just the absolute value of PQ. So there will be a familiar formula for finding the length of a vector that you'll see shortly. Okay, so a vector PQ can be used to describe the displacement of an object. That is, the object's overall change in position from point P to Q. So I need an apostrophe there, the object's overall change in position. Vectors are denoted in various ways. So the one that I'm going to use mostly, well, not exclusively, but often I'll just use lowercase letters with a rightward arrow above it. So this represents vector U, vector V, and so on. Another one is, as you've already seen, the initial point P and terminal point Q. So this is the vector PQ. There's another way to represent a vector. This is important, called the component form. So we have the coordinates A comma B in angle brackets. So left angle bracket A comma B, right angle bracket. This is the component form. This represents the vector whose initial point is 0, 0, or the origin, and the terminal point is the ordered pair AB. A vector in component form is said to be in standard position. since its initial point is the origin 0, 0. So I guess we could draw a picture here. So if you have an ordered pair AB in the plane, then if you draw the vector whose initial point is at the origin and the terminal point is at AB, then you represent this vector using the component form, the angle brackets A comma B. Okay, so this one is in standard form, standard position, I should say. Okay, well, vectors can be anywhere in a plane. They don't all have to start at the origin. So if the initial point of the vector AB is x1, y1, and its terminal point is x2, y2, then the standard position vector, or the component form, is found by subtracting one x coordinate from the other for the x coordinate and subtracting one y coordinate from the other for the y coordinate. So if the terminal point is x2, y2 and the initial point is x1, y1, then the first coordinate in the component form vector is x2 minus x1. The second coordinate is y2 minus y1. Okay, so in this example, this says find the standard position vector of a vector u that has an initial point at 1, -3 and a terminal point at 5, 2. Okay, so the vector u in component form then is the first coordinate is 5 minus 1, and the second coordinate is 2 minus -3. Then do the arithmetic. The component form is 4, 5. Okay, so let's graph both of the vectors. I always do that. I shoot myself in the foot. Okay, the vector u has an initial point at 1, -3, and a terminal point at 5, 2. Okay, so this is the vector u that when it's not in, well, this is one of the places it could be when it's not in standard position. But then if we write the component form, or if we graph the component form for 5, it's understood that the initial point is 0, 0, and the terminal point is 4, 5. So we note that the two vectors are equal, even though they're in different positions, because they have the same length and they have the same direction. Okay, but This one up here is in component form, 4, 5. And vector u down here is not in standard position. Okay, so to reiterate, two vectors are equal if they have the same direction and the same magnitude. The two vectors above are equal. Okay, given a standard position vector v, angle brackets a comma b, so that means the initial point is 0, 0. The magnitude is found, we denote the magnitude or the length as the absolute value of vector v, and it's just the square root of a squared plus b squared. So graphically, we could illustrate this by using the Pythagorean theorem, or equivalently just using the distance formula from the point 0, 0 to the point AB. That's the length of that vector, also called the magnitude. The direction is equal to the angle formed by the vector and the x-axis or the y-axis, depending on the application. So for our purposes, I don't have an exception. We're always going to form our angles with the x-axis because we're more familiar with that for now. The direction is determined by the equation tangent of theta equals b over a. So I'm sure you remember, but if you have a point AB and a component form vector whose initial point is 0, 0, then this value along the horizontal axis is A, this value along the vertical axis is B. If the angle is theta, then tangent of theta is equal to B over A. So that's a familiar quantity. If the terminal point of the vector is in the first or fourth quadrant, the angle is formed by the x-axis, and if the angle is formed by the x-axis, then theta is equal to the inverse tangent of b over a. Yeah, there's a note that I should make about this a little later. If the terminal point of the vector is in the second or third quadrant, and the angle is formed by the x-axis, then theta is equal to pi plus the inverse tangent of b over a. Okay, so in this example, let's find the magnitudes and directions of the vectors. Okay, so the vector in component form, two times the square root of 3 and 2, say. Okay, so we want to find theta. We also want to find the magnitude. So the magnitude that's the square root of the sum of the squares of the components. Okay, so when we square 2 times the square root of 3, we get 12, and then plus 2 squared is 4, so square root of 16, or 4. So 4 is the magnitude. And tangent of theta is equal to 2 divided by 2 times the square root of 3, which is 1 over the square root of 3. And we recognize that as theta equals pi over 6. Okay, so we're done. The length is 4, and theta is pi over 6. Okay, the next vector, -4, -6, well, this is in the third quadrant. So -4, -6, say. So we want to find theta. And also the magnitude. Okay, so the magnitude is equal to the square root of the number -4 squared plus the number -6 squared. So we get 16 plus 36 inside the square root. So the square root of 52. And this simplifies to 2 times the square root of 13. Okay, so that's the magnitude. 2 times the square root of 13. Tangent of theta is equal to -6 over -4, or +3/2. So the inverse tangent of 3/2 is in the first quadrant. So this angle right here is the inverse tangent of 3/2. But we want theta, and so theta is pi plus inverse tangent of 3/2. So I'll write that. Theta, we have to add pi to the inverse tangent of 3/2. Okay, the next one, find the magnitude and direction of the vector if its initial point is 4, -3, and its terminal point is -1, 2. Okay, so I think what I want to do, or what I would suggest doing, is write the vector in component form first. So the x-coordinate of the terminal point is -1, so -1 minus the x-coordinate of the initial point, -1 minus 4, and then the y-coordinate of the terminal point is 2, so 2 minus the y-coordinate of the initial point, 2 minus -3. And so the component form is -5, 5. Okay, so the vector is in the second quadrant. So -5, 5, say. negative 5, 5. And we want to find this angle, theta. Okay, well, the magnitude is equal to the square root of negative 5 squared plus 5 squared. So this is 25 plus 25. Square root of 50 is 5 times the square root of 2. Okay, so that's the length or the magnitude, 5 times the square root of 2. And tangent of theta is 5 divided by negative 5, or negative 1. The inverse tangent of negative 1 is in the fourth quadrant. This is the inverse tangent of negative 1. And we know what that is. That's one of our familiar quantities. This is negative pi over 4. Okay, but the theta that we want is negative pi over 4 plus pi. We also already know that theta is 3 pi over 4, but we can think of it as negative pi over 4 plus pi, which is 3 pi over 4. Okay, moving along. So in this space here, I'm going to show how to graph. If you're given vectors u and v, show how to graph u plus v, which is just another vector, and u minus v. So let's see. I'll have two different drawings. So on this one, let's suppose we have vector u here and vector v there. So how do we graph u plus v? Well, what we can do is we can remember vectors can be moved around as long as they all always point in the same direction and have the same length. So if I take the initial point of vector v and put it at the end point of vector u, so I hope this is at least believable. This is vector v. So if I want to add u plus v, then I just connect after I move the initial point of vector v to the end point of u. Then u plus v has an initial point at the initial point of u, and its end point is at the end point of vector v. So this is u plus v. You might see this referenced as the parallelogram rule for adding vectors. So if you construct a parallelogram, then the vector along one of the sides added to the vector on the adjacent side is just the diagonal of the parallelogram. Okay, well, how do we subtract vector u minus v? So let's see. I want to do it so I don't mess it up too bad. Okay, so suppose this is my vector u, and this is my vector v. So first note that if I add u to the vector negative v, that's equal to u minus v. Okay, and the vector negative v is just the vector that's in exactly the opposite position of v. So this is negative v. Well, I knew I would foul it up. So I'm going to take the vector negative v and translate it so that the initial point of negative v is at the end point of u. So this is my vector u, and I'm going to add u plus negative v. So u plus negative v is this vector, but u plus negative v is just u minus v, if you get the idea. Well, if you have vectors u and v in component form, such as in this example, then u plus v is found just simply by adding the corresponding components. So for u plus v, we can write 4 plus negative 2 for the first coordinate, and then 1 plus 3 for the second coordinate. And then do the arithmetic, we get the component form vector, or the standard position vector, 2, 4. That's u plus v. And u minus v, it's component-wise subtraction. So for the first coordinate, it's 4 minus negative 2. For the second coordinate, it's 1 minus 3. And then do the arithmetic. 4 minus negative 2 is 6 for the first component. 1 minus 3 is negative 2 for the second coordinate. So one of the things you could do to illustrate the drawings above, if you somewhat carefully construct component vectors 4, 1 and negative 2, 3, then you can illustrate that u plus v and u minus v look sort of like what we did above there. Okay, scalar multiplication. We've already actually applied scalar multiplication. I just didn't expound on it. So if we let k be a real number, which is referred to as a scalar, and if we let the vector u be in component form ab, then if we multiply the vector u by the scalar k times the component vector ab, we multiply k times each of the components. So it's k times a times comma k times b. Okay, so in this example, if the vector u is in component form 2, 3, well, it says graph 2u. So first, let's write that 2u is 2 times the component form vector 2, 3, which means multiply 2 times 2 for the first coordinate, 2 times 3 for the second coordinate. The negative of u, that's just -1 times the vector. So this one is -2, -3. Okay, so if we graph these vectors, yep, I never learn. Hey, the vector 2, 3 is right here. So this is vector u. And vector 2 times u, well, that's 2, 3, 4, 1, 2, 6. So it's about right there. It's supposed to be twice the length of u. And then negative u is -2, -3. So this is roughly negative u, negative of vector u. Okay, it's not too hard. And this next one, given u equals 4, -3 in component form, and the vector v in component form is -2, 1, then we can form a new vector w if we multiply u by 2 and multiply vector v by 3. So we can do all of this at once. The first component for w is 2 times 4 plus 3 times -2, or 8 minus 6, which is 2. Then the second coordinate, 2 times -3 plus 3 is -3. Okay, next page. Unit vector. A unit vector is a vector with a magnitude or a length of 1. So if vector v is a non-zero vector, then if you divide vector v by its length, then that is a unit vector in the direction of the vector v. Okay, so any non-zero vector divided by its magnitude is a unit vector. So here's just a short proof. If we let okay, so if I just have vector v, we know that the length or magnitude is the absolute value of v. So if you divide vector v by its length, well, this is just another vector. Let's call this vector w. So how do you find the length of w? Well, you just take the absolute value of that vector. But the absolute value of the vector v divided by the absolute value is just the absolute value of v over the absolute value of v, which is equal to 1. So that's the That's just a simple way to prove that if you divide a vector by its magnitude, you have a unit vector, which means that its length is 1. Okay, so find a unit vector in the same direction as the vector in component form 4, 7. Okay, so if I refer to the unit vector as u, then I just divide the vector 4, 7 by the length of that. And then the length of the vector 4, 7 is the square root of 4 squared plus 7 squared. Which is, you could write it as the vector 4 over the square root of 65, comma 7 over the square root of 65. Two important vectors are sometimes called the standard basis vectors for a two-dimensional space. So this vector I, it's a special vector, and it's 1, 0. So 1, 0 is on the positive x-axis, and then the other one is the vector j, which is on the positive y-axis. They are both unit vectors, and as I mentioned, vector I is in the direction of the positive x-axis, and vector j is in the direction of the positive y-axis. So any vector can be expressed as a linear combination of vectors I and j. So it's not really hard to do. If you have a vector v in component form, a comma b, then v equals a comma b. That's just equal to a times 1, 0 vector. This is the vector I plus b times 0, 1, or a times the vector I plus b times the vector j. Okay, so it's pretty easy. Write this vector that's in component form, -3, 5, in terms of unit vectors I and j. So you can do it all at once, or you can do it in a couple of steps. You can write this as -3 times the component form vector 1, 0 plus 5 times the component vector 0, 1. But this component vector 1, 0 is the vector I, so -3 times the vector I, and then plus 5 times the unit vector j, plus 5 times the unit vector j. And we're done. That's the answer. Hey, some other notation that you might see if you end up in calculus 2 and 3, then you'll see some of this stuff. And it should make sense. Given a standard position vector v, x comma y in angle brackets, with its direction angle theta, then we can show geometrically, and you've seen this a few times already this semester, cosine of theta is equal to x divided by the length of v, or x, which is this component x, it's the length of v times cosine of theta, and sine of theta is equal to y divided by the length of v, or y is equal to the length of vector v times sine of theta. So if you put all of that together, using vectors I and j, the vector v is x times the vector I plus y times the vector j. This is what we saw above. And then if you want to replace x with the length of vector v times cosine theta, you get this part, and then plus the y coordinate, the y component, the length of vector v times sine of theta times vector j. Okay, the last topic for the summer session is the dot product of two vectors. And this is pretty easy. The dot product of two vectors in component form. So if the vector u has components a, b, and if the vector v has components c, d, then the dot product is the sum of the component-wise vectors. So the dot product, this is more than just, this doesn't simply mean multiplication. So if we have the dot product of vectors u and v, then from vector u, the left coordinate a is multiplied by the left coordinate from vector v. So a times c, and then plus the product of the right coordinates. Okay, and a special note is that the dot product produces a scalar, or a real number. So the dot product of two vectors is not a vector, it's just a real number. Okay, the angle between vectors u and v can be found by using the formula. So in this formula, this is the dot product of the two unit vectors. So this is the dot product of the unit vectors. So we're down to less than 3 minutes. I'll say a little bit more about this in a second, but let's calculate the dot product. If u is the vector -2, 4, why am I rewriting these? I don't know. And the vector v is -3, 1, then the dot product of u and b, you can write the dot product in component form too, -2, 4, dot product, -3, 1. So this is just -2 times -3 plus 4 times 1, or 6 plus 4, which is 10. Okay, so that's the scalar that's produced by the dot product. The unit vector, I should say the length of vector u is the square root of -2 squared plus 4 squared. 4 plus 16, this is the square root of 20, or 2 times the square root of 5. And the vector v, the length of vector v, is the square root of the number -3 squared plus 1 squared, which is the square root of 10. And so cosine of theta, where theta is the angle between the vectors, this is the dot product of the unit vector -2, 4 over 2 times the square root of 5 times or the dot product of the other unit vector, -3, 1 over the square root of 10. So we get in the numerator 6 plus 4 is 10. 2 times the square root of 50 is going to be 10 times the square root of 2. So cosine of theta is 1 over the square root of 2. And we recognize this, 1 over the square root of 2 is the same as the square root of 2 over 2. So theta is pi over 4. That's the angle between the two vectors. So I'll just say one more thing. It would have been fun to show that cosine of theta is equal to the product of the two unit vectors. But you might try it. Use the law of cosines to show that this is true. Okay, but we're a little over time, so that's all for today. Tomorrow we'll spend the entire 100 minutes reviewing for the final exam, which will be on Thursday.